A minute ago we said that actually if electrons are shared, we said that is equal to what type of chemical bond? That will give you a covalent chemical bond. And if electrons are transferred, that will give you what type of chemical bond? That will give you an ionic chemical bond. Okay. Now, why would an electron be shared, out of the goodness of their heart, or why would electrons be shared between atoms, or why would an electron be transferred? Well, at the crux of that is this idea of electronegativity. To me, electronegativity is like the tug of war. Tug of war. Okay? And as it turns out, actually, metals don't have much pull, and nonmetals pull the most. So nonmetals have the greatest tug of war for electrons. Okay, they tug. Metals basically give. If you're playing tug of war and you give the rope away, I guess you lose, right? Okay. So electronegativity is actually a measure of atoms that are joined together, and sometimes I'll tell students, so like we have atom A that's going to join to atom B, okay? We're going to get some sort of chemical bond here. And is that going to be, electrons are going to be shared, or is electron going to be transferred from one atom to another? And so that actually comes up with something we call their individual electronegativity values. So this is how this works then. Like I said, metals have low electronegativity values, low tug of war, they give their electrons away, and nonmetals suck in electrons. They have a high pull for electrons, electronegativities. Now, if you were going to pick only the main group elements, so that's what, the group A elements, okay? So what, you have your 2 columns over here and your 6 columns over here. Okay, ignore these B and kind of squish them together. What you would see is electronegativity increases the farther you get into the nonmetals, kind of makes sense. And if you're dealing with the same group, electronegativity increases as you go up. Okay, so that's how kind of the tug of war goes. Linus Pauling, I want to say, actually earned a prize, Nobel Prize, I think in chemistry, for coming up with these values. So these are electronegativity values. You can kind of see the increase as you go up, okay, and increase as you go from left to right. These are just for the how do I say, the group A elements. Oh, sorry, these guys over here, they don't play. These guys, these group A elements, we don't deal with them with regard to forming bonds with anything because they're inert. They don't like to form bonds. This is just another look at the electronegativity values. I will warn you that electronegativity, a few things. Electronegativity has this Greek letter chi. It looks like the letter X. That's the symbol for electronegativity. And sometimes you'll hear me call them Pauling values. Electronegativity values or Pauling values. Okay, another look at This one's actually kind of helpful. I refer to this sometimes because, well, you'll see here in a minute. There's like a little subtraction that you can kind of see how much of a difference there is between the electronegativity values of the atoms. So actually, if you want to put your finger on this, you can, because I'm going to refer to it. So I mentioned that electronegativity values then kind of set the stage for if you have a pair of atoms that are going to be joined together, are electrons going to be shared and create a covalent bond, or electrons going to be transferred and create an ionic bond? So let me see if I can pull this up right quick. Okay. So this slide already kind of says that, oops, is that what I want to say? Oh, that isn't what I want to say. I already did that. Sorry. Okay, it's like deja vu. This is the one I wanted. Okay. So I put this together ahead of time. I want to, let's turn our attention to covalent chemical bonds. A covalent bond is formed when electrons are shared, and the example we used was water. So we showed how the hydrogen and the oxygen share 2 electrons to form that covalent bond. So what we do is come up with something called a delta chi. Okay, see, I didn't introduce what that is. In physical science, anytime you see this triangle, that means that it's the Greek letter. We already did something like this, I think. Delta means change in, okay, change in, okay, or difference. And actually, the change in electronegativity, delta chi, change in electronegativity, that, remember the X is the Greek letter chi, is equal to, basically, we're going to take what the electronegativity value of atom A is, minus electronegativity of atom B, and we want what we just want the difference, so we're going to take the absolute value of that, and that is our electronegativity difference. So what this says is if you have large differences, then electron is going to be transferred. You're going to end up with an ionic compound. If you have small differences between your tug of war, then electrons are going to be shared. It's just a beautiful story. So back to our water, all right? I want to kind of isolate that bond, that covalent bond there on the right, if that's okay with you. If you go back to the previous slide, you'll find the electronegativity value for oxygen is 3.5. The electronegativity value for hydrogen is 2.1. We could apply that little formula in the upper right-hand corner, and we could do a little subtraction here, and we could come up with the electronegativity difference, or delta chi, is 3.5 minus 2.1. Now those lines, those vertical lines there are just the absolute value of. So we have a difference of 1.4, which is actually a little significant, but not enough to make electrons be transferred. Those electrons are shared. I want to now take a look at the ionic compound we looked at before. We saw an electron transfer always from the metal to the nonmetal, from the sodium in this case to the chlorine. If we were to look up their electronegativity values on the previous slide, you would find, remember, metals have low electronegativity values. Sodium's a metal, so it has electronegativity value of 0.9, chlorine 3.0. Now, if we come up with their electronegativity difference, we do a little subtraction, 3.0 minus 0.9, I get 2.1. And as it turns out, that 2.1 electronegativity difference is enough for an electron to be transferred from the sodium to the chlorine. If we compare it to the electronegativity difference down below of the oxygen and the hydrogen of 1.4, that's less. Electron was shared, not transferred, although not shared equally. So just in general then, we can make this sort of statement. Usually if you have 2 nonmetals, electrons are not going to be transferred. 2 nonmetals stuck together with a chemical bond, that's going to be a covalent chemical bond. Electrons are going to be shared. If, however, you have atoms that are bonded together, one is a metal and one is a nonmetal, you're going to look at that sort of tug of war sort of deal. And remember, the nonmetal has a lot higher electronegativity value, means it's going to pull on the electron a lot more. So electrons can be transferred then to the nonmetal from the metal. And then that chemical bond will be ionic. Dun, dun,